Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Design of Solid Waste Management System for Angamaly Municipality Jineesha George Superscript 1, Swathy Krishna Superscript 2, Johana Reji Superscript 3, Vikas Vincent Superscript 1 Superscript 2 Superscript 3 UG Students, Department of Civil Engineering ADI Shankara Institute of Engineering and Technology, Caleulated, India Harshananda T. and Assistant Professor, Department of Civil Engineering ADI Shankara Institute of Engineering and Technology, Caleulated India Abstracted tremendous increase in the municipal solid waste, MSW, has been observed with increase in the population and rapid socio-economic development. In India it has become a serious issue because there are a few proper disposal systems for the MSW in many of the cities in India. In the present Indian scenario, suitable disposal of these MSW is a big concern. In this paper the treatment and disposal of the MSW of Angamaly Municipality in Kerala is planned. The details of Angamaly Municipality including population and waste generation were collected from various sources. From the data collected, waste management facilities like incinerator and a compost plant is designed for treatment of the city MSW and a landfill is also designed to dump the remaining waste after composting. For Angamaly Municipality, the total quantity of MSW is calculated as 12.59 tons/day, and the average generation rate of MS/W has been calculated as 0.4 kg/capita/day for composting. Required numbers of aerobic windrows are found as 60 and for landfill, which is designed with cover and liner, plan dimensions found as 12 x 10 m with extra 25 m land around the landfill to set one of the components. The incinerator was designed with primary chamber dimensions 2.16 m x 1.23 m x 3 m. Keywords: Municipal Solid Waste, Landfill, Incinerator, Composting Plant. Introduction. Solid waste management is one of the essential obligatory functions of the institutional and urban local bodies in India. This service is falling too short of the desired level of efficiency and satisfaction, resulting in problems of health, sanitation, and environmental degradation. Most institutional areas in the country are plagued by acute problems related to solid waste. Due to lack of serious efforts by authorities, garbage and its management has become a tenacious problem. Barring a few progressive municipal corporations and institutions in the country, most local bodies and institutes suffer due to non-availability of adequate expertise and experience, thereby the solid waste is not properly handled, resulting into creation of environmental pollution and health hazards. It is reiterated that the local bodies lack technical, managerial, administrative, financial, and adequate institutional arrangements. As such, it is very necessary to provide proper guidance to such urban local bodies and institutes so as to make them efficient in managing the solid waste generated in their respective cities and towns. In the present scenario of waste management system in Indian cities, there is acute scarcity of a suitable solid waste treatment and disposal system. Although the Angamaly Municipal Corporation is trying its best for the appropriate solid waste disposal of the city, still there are many spaces for the improvement of the system with the help of proper technology and expertise. A well-designed solid waste management system can help not only in treating and discarding the waste but also in maintaining a better environment. Landfilling is the final discarding practice for municipal solid wastes, MSW, management, CPCB, 2008. Due to pre-treatment there is a transform in the composition and properties of the waste which will influence the degradation and settlement characteristics of wastes, Siddiqui et al., 2012. If the MSW is first composted and the residual waste after composting is discarded in a sound designed sanitary landfill, then the trouble of appalling environmental risk due to MSW can be treated with an excellent mode. Proper disposal of MSW is a necessity to minimize environmental health impacts and degradation of land resources. In developing countries like India, MSW is commonly disposed of by transporting and discharging in open dumps, which are environmentally unsafe. Systematic disposal methods are composting, landfilling and incineration. Studies indicate open dumping to be the management method for 90% of MSW in India. 7. However, the so-called landfill practiced in the country is mostly covering refuse in the dump site by soil, neither with proper technical input nor with treatment of the emerging emissions to water, air and soil. Two objectives for the pre-treatment and disposal of municipal solid waste: an incinerator, compost plant, and sanitary landfill is designed for Angamaly Municipality, so that a healthier and sustainable environment continues. This study aims to fulfill the following objectives to perform ultimate analysis of the solid waste generated in Angamaly Municipality. Design an incinerator, design of a compost plant, design of a sanitary landfill. 3. Study area. Angamaly is a municipality and the northernmost tip of the city of Kochi in Kerala, India. Situated about 30 kilometers, 19 miles, north of the city center, The area is the northern gateway to the commercial capital of Kerala and is an integral part of the Kochi metropolitan area. The town lies at the intersection of Main Central Road, MC Road, and National Highway IJERT 10 is 060076 www.ijert.org 253. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 544. MC Road, which starts from Thiruvananthapuram ends at Angamaly at its intersection with NH 544. It is located 10.196 degrees north 76.386 degrees east. It covers a total area of 28.24 sq.km. Angamaly has an elevation of about 30 m4. Solid waste management problems in Angamaly. Angamaly, like any other urban metro cities of India, has several environmental issues. Increasing population has resulted in overcrowding and congestion. Higher population and lack of space have resulted in the development of slums. This also have been identified as one of the solid waste problem because of lack of basic infrastructure like drainage facilities, solid waste clearance, etc. The urban land use in the city includes activities like residential, industrial, commercial, recreational, educational institutions, etc. All these factors which constitute an urban environment are also the principal factors contributing to the solid waste management problems experienced by the city. Some of the important environmental issues seen in Angamaly are air pollution, water pollution, high noise level and solid waste pollution. The air, the supplier of the essential oxygen, is also the recipient of effluents from the industries, transportation, households, commercial sectors, etc. These effluents include gases like sulfur dioxide, nitrogen dioxide, carbon dioxide, carbon monoxide, lead, suspended particulate matter and several others. In Ernakulam the surface water includes the major Periyar River. There are some lakes and small drainage running across the Ernakulam district. The waterways are the recipient of waste produced by domestic, industries and commercial activities. The dumping of waste has rendered it to an unusable state. Thus solid waste pollution is the main problem faced by the city. The management of huge quantity of waste generated by the city is an area of concern. The lack of adequate infrastructure to remove the waste produced by various activities has become a matter of concern. Uncleared solid waste on the roadsides and overflowing dustbins are a common sight in the city, generating several health and environmental issues. Characteristics of MSW. The composition of solid waste varies from zone to zone due to difference in activities at each zone. The quantity and composition of wastes from various zones is given in Table I and the percentage of individual components in the waste is pictorially represented in Fig. The total amount of waste generated is 12,580 kg/day. Table 1 composition of MSW components quantity, kg/day, percentage food wastes 10,044.32 79.78 paper 613.134.87 plastic 608.094.83 metal 44.065.35 glass 133.454 1.06 rubber and leather 188.85 1.50 inert 219.06 1.74 ashes 211.512 1.68 wood 492.26 3.91 domestic hazards 35.25.28 Fig 1, composition of MSW 6. Ultimate analysis. The ultimate analysis of a waste component typically involves the determination of the percent C, carbon, Hi, hydrogen, O, oxygen, N, nitrogen, S, sulfur, and ash. The ultimate analysis of the waste generated at different zones of the campus was performed based on the relative composition of various components at the source or waste generation points. The average moisture content, MC, of the food waste, paper, plastic, metal, glass, rubber, and leather and wood is assumed as 75%, 7%, 2%, 4%, 2%, 10% and 30% respectively. Table 2 Ultimate analysis per dry unit weight waste CHONS ash food 48 6.437.62.60.45.0 plastic 67.2 22.8 10 paper 43.56 44.00.30.26.0 glass 0.50.10.40.1 to 98.9 rubber 68 11.6 10 0.4 10.0 metal 4.50.6 4.30.1 to 90.5 wood 4.56.0 42.7 0.20.1 1.5 ash 26.3 3.0 2.0 0.50 268.0 based on assumed moisture content, MC, and weight of individual component of solid waste generated, the dry weight of each component is calculated using equation 1. Thereafter, The chemical composition of solid waste, kg of C, H, O, N, S, is calculated based on ultimate analysis data. Table 3 Ultimate composition of MSW component carbon hydrogen oxygen nitrogen sulfur ash percentage 21.2841.75 15.35.862.1265.577. Design of compost plant. A composting plant for size reduction and the stabilization of mixed organic waste should be located as close to the disposal site as possible. IJERT 10 is 060076 www.ijert.org 254. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Air required for aerobic composting from ultimate analysis. The formula for the Guwahati waste is CC454H19450992.5 and 16.5. Theoretical air required for aerobic composting is calculated by the formula 1 and 2 CaH BO-CND plus 4A plus B2C3D /40 equals ACO2 plus B3D /2HO plus DNH3 1. Oxidation of NH3 NH3 plus 2O2 equals H20 plus HNO3, 2. Theoretical total air required equals 587.64 kg/ton of organic matter. Actual air to be supplied equals 2x. Theoretical air equals 1175.2 kg/ton of organic matter for 2021. Total waste generate is equals 12,590 tons/day. Total air required for the solid waste equals 14,796.820 ton of air/day. Revenue from the compost. Total compostable waste equals 11.33 tons/day. Assuming total compost equals 50% of original volume. Total compost equals 5.67 tons/day. Price of compost in Kerala equals Rs 20 per kg. So, total revenue from compost equals Rs 113.3 per day. Dimension of the windrow composting volume required for composting equals total solid waste in kg/density equals 40.45 cubic meters. Considering air circulation arrangement and taking windrow height equals 2.7 m, width equals 3 m upper and 6 m lower. Length required for composting equals volume/height/2 x upper width plus lower width equals 12.15 m. As composting takes minimum 2 months, at least 60 numbers of windrows are needed for the whole city. Fig 2. Composting windrow 8. Design of landfill. Landfill is a unit operation for final disposal of MSW on land, designed and constructed with the objective of minimum impact to the environment. The essential components of landfill include a liner system at the base and sides of the landfill which prevents migration of leachate or gas to the surrounding soil. 2. A leachate collection and control facility which collects and extracts leachate from within and from the base of the landfill and then treats the leachate. 3. A gas collection and control facility, optional for small landfills, which collects and extracts gas from within and from the top of the landfill and then treats it or uses it for energy recovery. 4. A final cover system at the top of the landfill which enhances surface drainage, prevents infiltrating water and supports surface vegetation. A surface water drainage system which collects and removes all surface runoff from the landfill site. 6. An environmental monitoring system which periodically collects and analyzes air, surface water, soil gas, and groundwater samples around the landfill site. And 8. A closure and post-closure plan which lists the steps that must be taken to close and secure a landfill site once the filling operation has been completed and the activities for long-term monitoring, operation, and maintenance of the completed landfill. The primary objective of landfill site design is to provide effective control measures to prevent or reduce as far as possible negative effects on the environment, in particular the pollution of surface water, groundwater, soil, and air, as well as the resulting risks to human health arising from landfilling of waste. Therefore, the design should consider all environmental media that may be significantly impacted through the life of the landfill. The chosen design will have a major influence on the operation, restoration, and aftercare of the facility. 1. Basic data location. Angamaly waste, non-biodegradable, 1,221.2 kilograms per day. Design life 5 years. Topography flat ground water table 10 m below ground surface. 2. Landfill capacity, height, and area. Current waste generation W equals 445,738 kilograms. Estimated rate of increase of waste generation per year, X equals 1%. Estimated waste generation after 5 years equals W, 1 plus X, N equals 445738, 1 plus 0.01. 5 equals 46,475.12 kilograms. Total waste generation in 5 years equals 0.5, W, 1 plus XN, N equals 2285.5 T. Total waste volume VW equals T slash 0.85 equals 2285.5 slash 0.85 equals 2688.8 cubic meters. Volume of daily cover equals 0.1 times VW equals 268.8 cubic meters. Volume of liner and cover system VC equals 0.25 times VW equals 672.2 cubic meters. First estimate of landfill volume CI equals VW plus VC equals 2688.8 plus 672.2 equals 3361 cubic meters. Likely shape of landfill rectangular. Possible maximum height of landfill equals 10 m. Area required equals 3361/10 equals 336 square meters. Approximate plan dimensions equals 28 m times 12 m. 3 landfill section and plan. Landfill section and plan is evaluated by providing a side slope of 4:1 and 2:1 respectively, for the portion above ground surface and the portion below the ground surface. The material excavated from the site is used as the material for daily cover. IJERT 10 is 060076 www.ijert.org 255. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Liner and final cover. Extra space was provided around the waste filling area for infrastructural facilities. 4 landfill phases. Active life of landfill equals 5 years. Duration of one phase equals 1 year. Number of phases equals 5. Each phase extends from base to final cover. Volume of one phase equals landfill capacity /5 equals 3361/5 equals 672.2 m. Plan area of phase equals volume of one phase landfill height equals 672.2/10 equals 67.2 m. 2 number of daily cells equals 365. Plan area of one cell on the basis of IM lift of each cell equals volume of one phase /365 equals 67.2 times 10/365 equals 1.84 square meters. Temporary holing area, excavated portion have to be used. Surface water drain, adjacent to arterial road along periphery. 5 liner and leachate collection system. Liner system, as per FAIO 9, the liner system will comprise of the following layers below the waste: 0.30 m thick drainage layer comprising of batter per sand 55 coarse sand or gravels, 0.2 m thick protective layer of sandy silt, 1.50 mm thick HDPE geomembrane, 1.0 m thick clay layer. Leachate collection pipe diameter of HDPE pipe, perforated, equals 10 cm. Spacing of one pipe required equals 2 m. Leachate holding tank size of holding 3 days. Leachate equals 7 m. 4 m. 3 m. Leachate treatment facility, 40 m * 20 m, in plan, tentative. 6 cover system design. A. Cover system, as per FAIO 9. The cover system were designed in 3 layers above the waste, i.e. 0.45 m thick gas collection layer comprising of gravels, 0.6 m thick barrier layer, sandy silt plus 5% bentonite, 0.3 m thick surface layer of local topsoil for vegetation growth. B. Passive gas vents. Passive gas vent of IM height side, above the ground level, will be provided at a spacing of 10 m. 9. Design of incinerator. Incineration may be defined as the thermal destruction of the waste at elevated temperature, say 1200 OC to 1600 OC under controlled operational condition. The products of combustion are carbon dioxide, water, and ash as a residue. The unit in which the process takes place is termed as incinerator. Properly controlled incineration is an effective means of reducing waste volume. It ensures cleaner and more complete combustion of waste and lends itself well to waste disposal in areas where population density is relatively high and availability of sites for landfill is low. Table 3. Quantity of biomedical wastes. SL no name of health. Quantity of establishment waste generated per day. PWR month 1. Private hospitals 184.8 kilograms 5,544 kilograms. 2 health centers 4.305 129.15 total 189.52 5,673. The following steps were used to design the incinerator. Each step of the design procedure has been discussed in great details, including the assumptions involved in the design process. 1. Design of primary chamber. For designing a primary chamber of multiple chamber incinerator under controlled air conditions, initially volume of primary chamber is to be determined so as 200 kg/day is dumped and the volume of heap is considered. For designing a primary chamber of multiple chamber incinerator under controlled air conditions, initially volume of primary chamber is to be determined so as 200 kg/day is dumped and the volume of heap is considered. Volume of heap, for 200 kilograms of waste, equals 8 cubic meters assuming suitable depth of 3 m. Volume equals 8/3 equals 2.66 square meters. Assume ratio of length and beat as 1.75:1. Therefore L/B equals 1.75/1 equals 1.75. L equals 1.75. B dimensions of primary chamber equals LBH area equals LXB 2.66 equals 1.75. B asterisk B 2.66 equals 1.75. B superscript 2. B equals 1.23 m. L equals 2.16 m. H equals 3 m. Hence, the dimensions of the primary chamber are 2.16 m x 1.23 m x 3 m x. Conclusions. The characteristics of solid waste generated in Angamaly Municipality was analyzed for their quantity and chemical characteristics. Ultimate analysis indicated a carbon content of 454 kg/ton of solid waste. It indicated the lowest occurrence of sulfur in the municipal solid waste. Composting should be adopted for the management of biodegradable portion of solid waste. Non-biodegradable portion of waste can be properly disposed into a landfill. Design of incinerator, composting plant, and landfill will be an excellent idea for municipal solid waste treatment and disposal in Angamaly Municipality. It will surely create a healthy environment, and also less land will be required for waste dumping, which will be beneficial for future. As the landfill is nearer, transportation cost will be less and economical. IJERT 10 is 060076 www.ijert.org 256. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 References 1 Guidelines and Checklist for Evaluation of MSW Landfills Proposals with Information on Existing Landfills, 2008, Central Pollution Control Board Ministry of Environment and Forests, Paribj Bhawan, East Arjun Nagar, Delhi 11032, August, 2008 2 Gulhati, SK, and Data, M, 2012. Geotechnical Engineering, Tata McGraw-Hill Education Private Limited 7, West Patel Nagar, New Delhi 110,088 3 Kosik, K, and Bhattacharya, A, 2012. Municipal Solid Waste Management and Energy Recovery from it, a case study of Guwahati, Assam for Manual on Municipal Solid Waste Management, 2000. Ministry of Urban Development, Government of India 5 Siddiqui, AA, Richards, DJ, and Powery, W, 2012. Investigations into the landfill behavior of pretreated wastes, Waste Management 32 2012, 1420-1426 6 Smith, M, and Aber, J, 2014, Heat Recovery from Compost, A Guide to Building an Aerated Static Pile Heat Recovery Composting Facility, UNH Cooperative Extension, June 2014 7 Varma, R.A., Status of Municipal Solid Waste Generation in Kerala and Their Characteristics, Executive Director, Sukatway Mission 8 Sunith Kumar, Blessy Merlin Kee Saw Shandarkar, AG, and Najaba, BS 2004. Hospital Waste Management. Paras Medical Publishers, 2nd edition. 9 Coker, AOETAL 1999. Characterization and Management of Solid Hospital Waste, 25th WEDC Conference, Addis Ababa, Ethiopia, page no 331-334 10 Central Pollution Control Board 2000. Manual on Hospital Waste Management, March, 2000. IJERT 10 is 060076 www.ijert.org 257. This work is licensed under a Creative Commons Attribution 4.0 International License.